So that's the first part of just getting an intro as to what we're doing right now. Now, in order to actually proceed, we will be doing a number of things. Now, one of the ways in which we will be communicating, or rather I will be communicating with you, will be using Google Classroom. We'll be posting most of the materials that you require, and also the things that you should be doing in Google Classroom. So one of the things that I would suggest that you do is all the time, check your Google Classroom every day in the morning, every day in the evening. So the usual regular school times is a good time to take a look at it so you can see what is posted. I will also post most of the material that you need over here, and you can see it on the sidelines. As we add more material to come over here, that's something that you would notice. Now, to start the course, we will also, on occasions, we will be using the Google Meet so that we can have a conversation. Or if you have any questions or concerns, you can actually type in your concerns or send an email. Then we will be able to deal with it. I have posted these videos over here. And if you go down to Equilibrium Lesson 1, which is continuation of what we actually we're doing in class. So you will notice that I've posted some material here which you can actually download. The first one is for the other class. The second one, Nelson, Equilibrium Topics. This is actually the outline of the sections that you have in your textbook so that you can correlate with the material that you are already given. So you can download this, and you click it. It should be you should be able to see. I just correlated it with a textbook so that you have textbooks with you, which you can use for your learning process. Now, I also have a PowerPoint presentation PDF file, which I'm going to show you right now, which you can actually download. So this is the first portion. It's not the complete PowerPoint presentation because we may not finish the whole PowerPoint today. So 1 to 26 I have actually posted here. I will post the rest as we go along. Now, you will have assignments which you will have to complete and post in Google Classroom that will be marked for completion. The whole point is we don't have a physical direct contact between each other, but we want to get engaged because you guys are going to university. And when you go there, definitely you need the subject knowledge that you should have gained in a classroom. But in this unprecedented circumstance, we cannot have that opportunity. So this is a nice experience for you to start your independent learning skills or develop your independent learning skills. That's what I would see it as. But still, you need all this knowledge that you need for your university study. For that reason, I would say take it seriously, engage in it, participate in the activities that are given, answer the quizzes that I will post. And that should give you an idea and a self-assessment as to what your abilities are in terms of the content. That is what we are really looking at. Your involvement, your engagement, your skills in developing independent study skills. That's what we need. Fundamentally, you being successful is when you go to university. And therefore, for that reason, I would say spend the time that you have. Now, you may have pressures at home. You may be working. You may be doing other things. You may be involved in family activities. Find time, and when you're convenient, in a convenient way, try to complete your assignments and try to be knowledgeable in terms of the content that you have. That's all that I can tell you. Now, if you look at the PowerPoint presentation, I kind of have divided the lessons into 5 topics here, not the total lesson, what we will be doing immediately. So topic 1 is reversible reactions. Topic 2 is law of mass action. Topic 3 is homogeneous and heterogeneous equilibrium. 4 is writing equilibrium expressions, and 5 is relationship between these two. So I'll just start the PowerPoint for you. Sorry about that, guys. We are just getting started. So there may be a little bit of glitches here and there. The first couple of days, we will try to iron it out as we go along. And then mostly it'll be posting of material online, so on your Google Classroom. So here we have. Now, I would always suggest that you have a notebook with you, a pen, a pencil, or a pen, calculator, a periodic table. All of these should be with you all the time so that as and when we need it, you can actually use it. So it'll be a good idea to actually make your own notes, not just for the sake of recalling, but you have this PowerPoint slide with you so that you can also use it. So today's lesson, we are going to actually define reversible reactions, equilibrium state, irreversible reactions, conditions for equilibrium, and the difference between irreversible and reversible reactions. That is what we're really going to look at. Now, the definition of a reversible reaction. It's a chemical reaction where the reactants form products. That in turn reacts to give the reactants back. So that's what we're looking at. So if you look at the equation that is given here, A and B can react to give you C and D. And again, C and D in turn can react to give you A and B. And you will see that the arrow that is used is two half arrows, one indicating the forward direction and the other indicating the backward direction. That is called reversible reaction representation, or we call it as double-headed arrow. Now, state of equilibrium. A state of equilibrium, whenever you have a reversible reaction, there will be a particular point in the reaction when apparently the concentrations of the reactants and products do not show any change. That's what we refer to as a state of equilibrium. So usually, if we have to achieve this equilibrium, we need to have a closed system. So one of the important conditions for achieving equilibrium would be to have a closed system. And then there is a point where the concentrations of reactants and products actually do not change a lot. And that state is what we refer to as a state of equilibrium. So here you can see a graph here. On the y-axis, you can see the reaction rate. On the x-axis, you can see the time coordinate. And we are going to look at a reaction where reactants are changing to products. Now, mind you, we have a closed system. I mean, Coke can, we have a seal, before opening it is completely closed. So you put a single reactant, only the reactant inside, close the container, seal it, and then we start the reaction. When you start the reaction, what happens? The amount of reactants will start decreasing. And this is the graph that shows the rate at which the reaction changes. I'm using the word rate, and I'm not using the word concentration here. So with time, what happens? The amount of reactants decreases, and the rate at which they decrease will also come down. So if you actually look at, give me a minute. So at this point, you'll find the rate of reaction is really, really high. At this point, the rate of reaction is really, really low. So the rate has decreased with time. So as the time progresses, we find there is a decrease in the rate of reaction, which means based on collision theory, we know that the rate of reaction depends on how many reactants are there in a given time. And with time, since the reactants are decreasing, the rate of the reaction will decrease. And finally, it will reach a horizontal portion over here. This is what we see here. Okay. Now, at the same time, when the reactants change into products, because we have a reversible reaction, the products are formed. The products really recombine to give you back the reactants. So we see that the red line indicates initially we had no product. And as time progresses, what happens? As the time is moving on, the rate of reaction, which means we are talking about the rate of the backward reaction, is actually increasing. And finally, it will reach a point where they both appears to be constant. Okay, that's what you see here. So this line forward is actually, it's appearing to be constant. So if you actually look at the graph over here, you'll find that there is a time when the rate of reaction becomes actually parallel to the x-axis. That's a state where we call the equilibrium state. So the equilibrium state would show that for both the reactants and the products, the rate of reaction can be measured off or read off from this point in actually the graph. So when the rates of reaction shows a constancy, that's when we refer to as a state of equilibrium. So reversible reactions, it takes a bit of a time for the reaction to take place. And after a while, the rate of change of concentration stops. It appears as if the reaction is not taking place at all. That's what really happens over here. And that state is referred to as a state of equilibrium. So this is the best way to actually see it. And it is not necessary that both the lines should meet. We could have the blue line slightly above and the red line slightly below, but the only condition is that they may actually be parallel to each other when the system achieves equilibrium. There are a number of images in your textbook, so review your textbook. You should have a clearer picture for that. Okay. So that's what this graph represents. So you should be able to draw a graph for a reversible reaction indicating the change in rate of reaction for the concentration of the reactants and products. An irreversible reaction. Now, these are reactions where you mix the reactants together and it gives you the products. But if you try to mix the products together, you will never get the reactants back in a single step. Such reactions are called irreversible reactions. They can go almost 99% completion for valid reasons. Now, a single-headed arrow is a way to represent the irreversible reaction. Now, we had talked about rate law and law of mass action when we had discussed actually rates of reaction. So we are again coming back to that. Again, the rate of a reaction is directly proportional to the product of the concentration of the reactants raised to their appropriate coefficients. This rate represents the rate of the forward reaction, where K is equals to A into A and B into raised to B. And again, rate of the backward reaction. C and D can start to react between each other to give back A and B, being a reversible reaction. So when the rates of the forward and the backwards show constancy, that was a state of equilibrium. So we're going to use this and come up with what we call an equilibrium expression. So if you relate to the two rates for the forward and the backward, we can rearrange it to obtain what we refer to as the equilibrium law, represented for the equilibrium constant calculation. So every time the system achieves equilibrium, because we have concentrations of reactants and products, which we can take them and substitute them into the law of mass action, which can be finally written as an equilibrium constant expression over here. Kc is equals to products over reactants raised to their appropriate coefficients based on the definition from law of mass action. This value, a numerical value representing the equilibrium state. The equilibrium state means the system has achieved equilibrium, which means the concentrations of products and reactants remain the same. The rates of the forward reaction and rates of the backward reaction shows constancy. That's what we mean by the state. So that can be written like this. Kc is equals to C, that is a concentration of C raised to lowercase c, which is the number of moles of C. So C and D are products, A and B are reactants. Now, here is an example where you can actually write the equilibrium constant expression. So you will be expected to write equilibrium constant expression. So here we have formation of ammonia, and it's represented using the equation Kc is equals to products over reactants. Product is NH3, and the coefficient of NH3 is 2, so it is raised to 2. And that's why we have this 2 is the 2 that we have over here. Nitrogen over here, coefficient is 1, therefore there's no number here. Hydrogen has a coefficient of 3, therefore square brackets raised to 3. Every time you put square brackets on this equation or this equilibrium expression, it represents molar concentration, which means moles per liter. So you should be able to write this expression. So I would suggest write down this Kc expression as an example in your notebook, so you just get used to the idea of writing an equilibrium expression. Okay. We have seen these words homogeneous and heterogeneous right from grade 9, grade 10. We had seen classification of matter. We have seen those words. So those things are coming back to us right now. We are applying them to equilibrium systems. So homogeneous equilibria, by looking at the reactants and products in the reaction that is given, here we are again looking at the formation of ammonia from gaseous nitrogen, gaseous hydrogen, giving you ammonia, which is again a gas. So the reactants and products are in the same phase. The technical word is phase. It means state of matter in a chemical reaction. Then The reaction is referred to as the homogeneous equilibria. The condition is the reactants and products should be in the same physical state. Here we have again a second reaction. Here N2O4, dinitrogen tetroxide, which is a brown colored gas, decomposes to give you nitrogen dioxide, which is colorless. And actually, if you combine 2 moles of nitrogen dioxide, you get dinitrogen tetroxide, which is a brown colored gas. Now, here is a second example, just to give you an idea of homogeneous equilibria need not be only for gases. It can also be in aqueous solutions. Reaction between iron 3 ions and thiocyanate ions, giving you a brown colored substance, FeSen2+. So if you write an equilibrium expression of products over reactants, yeah, there you go. You can get an equilibrium constant expression as indicated here. Heterogeneous equilibrium, again, which means the reactants and products are not in the same phase, which indicates that the reactants could be in one state and the products could be in a different state, or it could be vice versa. So the reaction that I have taken here is magnesium carbonate, which is a solid at room temperature. If you actually heat it in a closed container, it decomposes to give you magnesium oxide and carbon dioxide. Magnesium carbonate and magnesium oxide being solids, they are not included in the equilibrium expression, because what we're going to say is, how do we know the system is in equilibrium if we have a closed system where we have solid magnesium carbonate being heated? The only change that we can measure is the change of pressure. Therefore, merely by measuring the pressure of the container, we can say whether the system has achieved equilibrium or not. Therefore, when you're writing the equilibrium constant expression, we do not use the constants. We do not use the concentration of the solids in this case, or we do not include the concentration of the reactants that are present in large quantities. Now, when you write the equilibrium constant expressions for it, since we do not include it, the equilibrium constant expression, Kc, for the reaction that is given is CO2, the molar concentration of CO2. That's what we actually consider here. Again, let's look at a reaction between calcium ion and phosphate ions giving you calcium phosphate. This equation actually represents a net ionic equation for a double displacement reaction. So again, grade 11, double displacement reactions. So if you write the net ionic equation, you find calcium ions and phosphate ions combined to give you solid calcium phosphate. So this equilibria represents a heterogeneous equilibria. Now, when you write the Kc expression here, here I have written C, reactants and products are gases. So if I use molar concentrations, I can actually use square brackets. Gases being gases in a container, the total pressure exerted by a mixture of gases is sum of the partial pressures. Partial pressures, you have heard when you learned Dalton's law in gas phase reactions, which you learned in grade 11. So go and refer to Dalton's law if you have any doubt. So we can also change the molar concentration term here using partial pressures. That's what we're really going to do. So it is possible to convert Kc, the equilibrium constant that we have seen, which is calculated using molar concentrations, to equilibrium constant expression where we can use pressure or partial pressures. So that's an important thing that we need to recognize is possible. I would only expect you to know that it's a possibility at this point of time. If you can memorize the equation and solve problems, great. But I just wanted to show you that relationship does exist. So here we have a reaction again. I've taken the reaction of nitrogen and hydrogen giving ammonia. We know the equilibrium constant expression. I have used molar concentration, so square brackets on the numerator and denominator. So this would be a Kc expression. Now, because the reactants and products are gases, we can also replace the molar concentration with PNH3, which means the partial pressure of ammonia divided by the partial pressure of nitrogen divided by the partial pressure of hydrogen raised to the appropriate coefficients, which is 2 and 3. So if you're using partial pressures instead of molar concentrations, then the equilibrium constant is referred to as Kp. That's what we have here. So there is a relationship between them. We don't have to derive it, but it would be good to know how we can convert them. So the equation Kc is equals to Kp divided by RT raised to delta n. Or Kp is equals to this times this. Or we can say Kp is equals to Kc into RT raised to delta n. So one of the things that you can ask me is, what is R? R represents the universal gas constant, which is 8.314 joules per Kelvin per mole. You can write that down in your notebook. R represents the universal gas constant, 8.314 joules per Kelvin per mole. And temperature has to be used in Kelvin. And there is something called delta N. I'm going to show you how you can calculate delta N for the reaction. So delta N, you will see here, is for this reaction can be calculated by taking the number of moles of the gas products minus number of moles of the gas reactants. We only look at the gas reactants and products. So the products, ammonia, the number of moles, 2. Reactants, 2 gases. The first reactant, we have 1 mole. The second reactant, we have 3 moles. If you add the 2 together, it becomes 4. So delta N is equals to number of moles of the gas products, which is 2, minus number of moles of the gas reactants, 1 plus 3. So 2 minus 4 is minus 2. So any given reaction, if you are trying to convert Kc to Kp, if you have to calculate delta N, you will only look at the gas reactants. If there is a solid, that's not included in it. Okay, so that's an important condition. Reactants and products should be gases. I have a sample problem here just for you to see how it works. Determine Kp for the following reaction at 500 degrees Celsius. Mind you, I said the temperature has to be in Kelvin. If 500 degrees Celsius is given, you have to convert it into Kelvin before you solve it. Kc is 6.0 into 10 to the negative 2. R is given to you. So here, the R is given in liter atmosphere per Kelvin per mole. This is obtained from the ideal gas equation. Again, grade 11 gas laws. So just refer to this value. It will be given for you. You don't have to memorize it. We have the relationship here, and we have to convert the Kc to Kp. So Kp is equal to Kc into RT raised to delta N. So we already calculated delta N, which is minus 2. Kc is given 6.0. R is known. Temperature in Kelvin. Delta N is minus 2. So you would notice that in brackets, R and T are inside square brackets, where raised to delta N, which is negative 2. Kp again, we take the product of this, we get this value, and finally Kp is equal to 1.5 into 10 to the power of negative 5. So all it's showing you is that we can convert Kc to Kp. That's all. So at this point of time, I just want to just recall, we did reversible, irreversible reactions. We did law of mass action. We know what homogeneous and heterogeneous equilibria are. That's what we have done so far. And we made a simple conversion of Kc to Kp. So bear in mind all the important things that we have done at this point of time. Okay. Now, Le Chatelier's principle is a statement that can be recalled pretty easily. So we know that we have a system in equilibrium. So one of the conditions for a system to be in equilibrium is we need to have a closed system. Okay. So when a system in equilibrium is subjected to stress, the system readjusts so as to negate the effect of the stress. So every time we apply a stress onto a system, the system will actually perform some readjustments so that the effect of the stress is minimized. In chemical reactions, when we actually cause a stress, the reversible reaction always tries to change the direction of the reaction. That's what it is. So in order to do that, we will have to actually talk about what a stress is. Now, when we say stress in equilibrium, we have a closed system, we have reactants and products in it. When we say there is a stress, what we mean by it, we can add more reactants, We can add more products. We can take away reactants. We can take away products. We can change the pressure of the container by either changing the volume of the container, by compressing it or expanding it, or by adding more reactants and products, or by changing temperature. And you also know that the equilibrium constant, the value, or the equilibrium state is unique for a given temperature. Now, here is a reaction between nitrogen and hydrogen, the gases producing ammonia. We have a concentration Kc expression for it. So we want to see what would happen if you increase the concentration of the reactants. We can increase the concentration of a single reactant like nitrogen. So what do you think will happen? Now, when you increase the concentration of the reactants, in this expression over here, you'll find that we have more reactants in the denominator, which means if you actually calculate a numerical value for Kc, that's going to be altered. So naturally speaking, if you add more reactants to a reaction system, what do you think will happen? It'll form more products. So this is what we're going to do. We're going to use a language here, which will kind of explain what happens when we add more reactants to products. So imagine that this white little section is a closed container in which we have nitrogen and hydrogen, and we allowed the reaction to take place, and it achieved equilibrium. So there is the rates of reaction has reached a constancy. And if you write this expression and substitute the values of the molar concentration of ammonia, nitrogen, and hydrogen, it will show a constant value. We say the equilibrium constant has a particular number. Into that system, we add more of the reactants. So what we are really doing is we are making the denominator larger. When you make the denominator larger, the numerical value is going to be altered, which means the value of Kc is going to go down. Or it's no more Kc, it's going to be concentration quotient. We'll be seeing it later. So what do you think the system can do? So in order for the system to achieve equilibrium, what will happen is it will start combining to form more products, so the numerator becomes larger. And at the same time, the denominator becomes smaller. And then again, it will strike a new balance. So if you add more reactants to the system, what will happen is it will form more products. So one way to increase the amount of products in reversible reaction is increasing the reactants. So reversible reactions, if you have a closed system and the system has achieved equilibrium, you can cause a stress by adding more reactants. Or we can add more products. If you add more products, what do you think will happen? Since the numerator is larger, we have a larger amount of products. Immediately, the backward rate of reaction increases and more nitrogen and hydrogen will be formed. Or we would simply say the equilibrium would shift left. If more products are formed, we would say equilibrium will shift right. And if more reactants are formed, we would say equilibrium would shift left. I want you to recall here from what we have talked about so far. I know it's a little bit of time. First is you should be able to write equilibrium constant expressions, which means you should be able to write Kc expressions. That's one thing you have to do. Second one I want you to do is you should be able to identify homogeneous and heterogeneous equilibria. By looking at the reaction, looking at the subscripts, if they are different states, you should be able to do that. Third skill is you should be able to write Kc and Kp expressions, which means when you write the Kc expression, you will use square brackets with molar concentrations. And if you're using Kp, use partial pressures. Converting Kc to Kp, the equation that I've given can be used. That's one way for doing it. So at this point, I want you to make a note in your notebook. You should write your own definitions for reversible reactions. Irreversible reactions. Write the statement for the law of mass action. Identify homogeneous and heterogeneous equilibria. Write equilibrium expressions, converting Kc and Kp.